Okay, so we'll do some problems related to oblique shock interaction and shock reflections. So one problem I have right now with some this is we are going to talk on reflection of oblique shock. We have a tutorial question right now. So I have a flat plate. There is a Mach number which is greater than 1. There is an oblique shock that is sitting here, probably made due to some wedge that is somewhere here. So it creates an oblique shock, it comes, reflects at the surface, and then there is a reflected shock, reflected oblique shock. So the wave comes here, take a turn, and then again turns it along with the flow. So the values I have here is m equals 2.5. So m1 is 2.5 and turns an angle of 4 degrees. Okay. So your theta is 4 degrees is what it means. Find the Mach after the reflected shock. So this is my incident shock and this is my reflected shock. So it comes and turns by 4 degrees. So this is my 4 degrees. So the fluid comes and because of the shock it turns by 4 degrees and then gets back to the flow direction that is parallel to the surface. So what is the Mach number after this? So if I call this 1, region 2 and region 3, the question is to find M3. So if I draw the first shock, the fluid comes and make a turn. This is 4 and M1 is 2.5. So I can find the beta from theta beta M chart. So for theta equals 4, m equals 2.5, I would get a beta which from the chart, if I look for 2.5 and theta equals 4 degrees, I would get an m beta to be around 0.3. Okay. So, my beta I would get it as 26.5. So, this is reflected by another shock which turns the flow direction parallel to the surface. So, this turn angle is also 4 degrees if it want to have a line parallel to V1. Okay. So, your theta 1 is same as your theta 2 is 4 degrees. Now, you can get from region 1, region 2 and region 3, I can get M1n, which is nothing but M1 into sin beta 1, which is 2.5 sin 26.5. 1.12, no? Be 1.12. If I know M1n, I can get M2n from normal shock tables. So, my M2n 0.897. Now, if I know M2n, I can get M2 from sin beta minus theta, which is beta 1 minus theta 1. Okay. So, this is M2n as 2.3. Okay. So, this is approximately 2.3. So, what did I get now? So, I have a shock B1, then it turns, this angle is 4, this angle is 26.6, M2 is 2.3, M1 is 2.5 and the M1n, and I got M2n. Okay. Now, this velocity is going and hitting another shock wave which turns the direction parallel to the surface. Okay. So, this velocity turned by 4 degrees. This is the second shock wave. So, this is the reflected shock wave. This is the incident shock, this is the reflected shock. So, this M2 is now 2.3 turned by 4 degrees to this. So, if I want to find M2 is 2.3, theta 2 is 4 degrees, I do not know this beta 2. So, how do I get beta 2? I look at theta beta m chart to get beta 2, which is 28 degrees. Okay. So, this angle is 28 degrees. So, I look for this M2 and this theta, I get a beta value which is 28 degrees. So, my M2n that is going to hit this, hit the second shock would be m2 into sine beta 2. So, n2 of the reflected. So, beta 2, this would be beta 2. The angle with which it comes and hits the shock, and the angle between the velocity vector and the shock is your beta 2. Okay, so m2 is m2n is normal to this. So, m2 into sine beta 2 would be your m2n, which is 1.08, which would give me a m3n from shock tables 1.928 from shock tables. Okay. So, now I have m3n which is 0.928. If I have m3n, my m3 into sine beta 2 minus theta 2. So, my m3 is 0.928 divided by sine beta 2 is 28 degrees minus 4 degrees. So, this would be 2.28, all taking the weak shock solution. Okay. So, this beta and beta 1 are from the weak solution. So, I have a reflected angle, and then this m2, m3 is 2.28. Okay. So, from the problem, if you look at it, I have m1 is 2.5, turns by 4 degrees and then turns again to m3. m3 is calculated to be 2.28. Okay. If you know these values m1, m2 and m3, you can find the corresponding pressure ratios. So, if I know pressure P1, I can find P3 from m1n and m2n, and then m2n and m3n. Okay. So, the pressure across this shock is known, the ratios are known. So, I can find P1 by P3 to be P3 by P2 P1 by P2 into P2 by P3. Okay. So, this is across the first incident shock, this is across the reflected shock, okay, from M1n and from M2n of the reflected shock. Okay. If you know this, then you can, P1 is given, so you can find P3. So, that is this particular problem. Similarly, you can do another tutorial. So, my flat plates then suddenly encounters a ramp, and there is a top wall here. So, this is by some theta. So, I know my M1. So, it creates a shock, oblique shock. It goes and hits the top wall. and it reflects. So, this velocity vector turns by theta degrees, goes and hits the second reflected shock, then again turns back to the line parallel to your surface. Okay, so this is not normal to this. So, it will be at some angle and then turns. So, I have M1 coming and hitting M, and the resultant Mach number is M2, and then I get M3. This is similar to the problem what we have done. Its theta reflected value is the same. So, this deflection is the same as what you have here. Okay. So, the same deflected value, from which you can find from the same procedure what we have done. It is exactly the same problem, except that whatever we have done here, it is on the top side. So, it is the same problem. Okay, so, you can evaluate M2 as M3 as what we have done before. Now, if the top surface is also at some angle, so I will not evaluate these problems, I am just demonstrating that it can be done with the same kind of analysis. So, I have a surface at, say, let us put it as theta 1. So, it generates a oblique shock. So, this is a surface, and this top surface also turns by some angle theta 2. Okay. So, there is a shock that comes, and at this point itself the surface turns, and because of which there is another shock wave that is here. So, I have V1 or M1 approaching the first shock, then it turns by theta 1, it goes and hits this surface, then it turns theta 1 and theta 2. So, the turning angle here is going to be theta 1 plus theta 2. So, if you realize that this angle is theta 1 plus theta 2, the problem is same as what we have done before. Okay. Find beta, find the normal one, find the shock. So, find beta 1, from which I would get Mn1, from which I will get Mn2, from which I would get Mn2, and the moment I get Mn2, I get Mn2n for the reflected shock, and Mn2 I would get Mn3, from Mn2, from M2 and theta 1 plus theta 2 I would get beta 2, and I would easily get M3n based on M2n divided by sin beta 2 minus theta 1 plus theta 2. So, I would get my values at M2n. So, the procedure is the same thing as we have done before, just that you have to realize this angle is now turned for theta 2 also. Okay. Okay. Now we are going to discuss something called series of shock wave. So if I have series of shock wave, what would be the Mach number after that? So if I have a plate, I have a first shock, then I have another shock, then I have yet another shock. Okay. So there are the angles of which are different. So this, so I have M1 here. So it is turned by some angle theta 1. So the shock angle, this is beta 1, then this would be my beta 2. It goes and hits another shock wave with beta 3, and the turn angle is again different, theta 2, and this again say suppose it turns back to the original position, this would be my theta 3. So I have series of solution. What would be my loss in stagnation pressure instead of having it as one strong wave? So if I can have M1 reduced to M3 by single wave, M1 reducing to M3 by series of shock waves, what would be the loss in stagnation pressure? So this is something which typically known as the phenomena of or the technique of pressure recovery. So you want to reduce your Mach number from M1 to M3, but you do not want to lose your stagnation pressure. So instead of having one single strong shock wave, you reduce that to series of oblique shock wave, retain your stagnation pressure as much as possible, but all the way reducing M1 to M3. Okay, so that is the typical technique here. So if you can put some numerical values and see how it reduces. Okay, so this happens typically in a gas turbine engine, where I have an inlet. So if my oncoming Mach number is greater than 1, there will be a strong shock sitting here. Okay, and this is one single shock. So this would be P0x, which is reduced to P0y, and this Mach number behind the shock would be subsonic, and you have a subsonic flow inside the diffuser. Instead of this, the usual technique is to so if I have a engine here, a very high Mach number is coming. So instead of having a strong shock here, I would attach something like this in front of the diffuser inlet. So I would have a shock here. Okay, so I have a oblique shock here. Now oblique shock will have a supersonic Mach number behind the wave. So that would create another shock here. So instead of one strong shock, now I have two shocks here. So the pressure jump, the pressure P0x to P0y is done in a series of shocks. So your P0 you can reduce it very minimal value, or you can retain your P0 to as much as possible even when reducing your Mach number to something subsonic. So instead of this two shocks, I can have yet another series of oblique shock. Okay. So I have series of oblique shocks here. So there will be one shock here, there will be another shock here, there will be another shock here. So at this series of shocks, I can take my Mach number, reduce my Mach number to subsonic Mach number even when keeping P0 the same value. So, P0 is the total, it is an indication of how much work it can do. So, you want to maximize that and you want to gain a compression inside the diffuser as much as possible. Now, in compression shock wave you are actually compressing, you are increasing your pressure. So, you want to gain that, you want to do that here, yet you do not want to lose your P0 x or the stagnation pressure. So, you can do that a numerical problem here. So, let us try to work it out. So, I have one oblique shock here, then somewhere here I have a normal shock. So, this is something called a cowled region. So, that is where you have the fluid that is going through towards the compressor. Okay. So, this is the diffuser or the inlet of the gas turbine engine. So, you have a oblique shock that is sitting here. The wedge angle is given 10 degrees. So, this is 20 degrees. So, the wedge angle the beta or the theta or the turn angle is 10 degrees. So, I have M1 3 theta equals 10 degrees. So, I can find M2. So, I divide this region as region 1, region 2, region 3 and 4. 3 is before the shock, 4 is after the normal shock. So, I can find M2. For that I would get beta, then I would use M1n, then I would compute my M2n, then I would get my M2 from the normal shock and the oblique shock tables. Okay. So, up to this is from theta beta m chart, this is from normal shock table, and this is from the chart. So, if you the question is to find m dot and P04 by P01. So, the moment you have M1n, you can find M1n, I can find P02 by P01. So, from A3 by A3 star, meter square. So, the area where the shock, normal shock forms is 0.12 meter square. Okay. So, I can compute A3 by A3 star as A3 by A2 into A2 by A2 star into A2 star by A3 star. So, A2 by A3, A2 up from A2 to A3 it is isentropic flow. So, A2 star and A3 star are the same. So, from 2 to 3 is isentropic flow. So, my A2 star is same as my A3 star. A2 and A3 are given. A3 is 0.12 divided by A2 is 0.1 into A2 by A2 star of associated with M2 and this is 1. Okay. So, I come back and put the values here. The M2 is, what is M2? 2.48, M2N is 0.746 and M1N 1.385, beta 27.8. So, from beta I would get M1N and M2N from the normal shock table, from which I can compute M2 as 2.48. So, this M2 is 2.48. So, if I know this value, I can find M3. Star is into, what is this value? A2 by A2 star at 2.48. This would give me an M3 from the isentropic tables. Eh? 2.58. 588, and this value is 10, and this corresponds to a Mach number eh? 2.67 from isentropic tables. Okay. If you know M3, I can find M2 from shock tables, which is for this Mach number there is a shock at 3 and 4, M3 is 2.64 and the normal shock 0.498. Okay. This will also give me a P03 by P04 0.431, P4 by P0, 4 by 3. P04 by P03 is 0.431. Okay. So, the question is to find P04 by P01, which is P04 by P03 into P03 by P01. So, this is associated with the shock relation, which is 0.431. This is associated with, so this is with mx equals M3, and this is associated with the oblique shock. M2n, mx equals M1n, which is 1.38. M1n, which is 1.38, which is 0.414. So, that would be the ratios P04 to P01. So, final answer is this is so let me see if okay. So, m dot you can compute from rho 2 A2 V2. So, A2 is given, V2 and rho 2 you can compute from P2 by rho T2 into A2 into M2 into root of gamma R T2. Okay. So, T2 T is given, okay. So, you have to know T to get the values. Okay. So, if you know your T2 you can get your m dot. Okay. So, if I along with the inlet Mach number, if I give my P1 and T1, I can compute the final pressure and temperature and also the m dot that is going through the cowl. So, you could devise your own examples with whatever we have discussed here. So, series of oblique shocks are going to give a P0 recovery, and the other problems which you had just now with the reflected and the other shock. So, for the nozzle flow in an overexpanded nozzle, or if I have this shock, this kind of flows which will reflect two shock waves, and then I have another set of shock waves. So, I have a flow here M1 greater than 1. So, there is shock 1, shock 2, 3 and 4. This is region A, B, C and D. Okay. So, first reflection is very straightforward, you can do. Then the second reflection also you can somewhat, some of the things are true, but then here you will have two slip lines. Okay. So, you have to do iteratively to get this particular region where you have the pressure in D, say for example 3D, and pressure along 4D are the same. Okay. Pressure due to the third shock and pressure due to the fourth shock in the slip plane is the same, and the velocity is in the same direction. So, you have to iteratively do this. So, we are just not trying to do that numerical problem here, but it is possible to do evaluate that if we have enough time or a computer with us. Okay. So, that brings us to the end of the discussion with shock oblique shock waves. In the next class onwards, we will discuss something called the expansion fan, and that would be our last topic of discussion. Okay.